lecture we were talking about velocity of waves, and we said wave travels both in distance and time. So if t is the time period and lambda is the wavelength, which means in each cycle is covered in capital time time capital T, and each cycle covers lambda distance in one cycle. The velocity is given as lambda over t, or you can also say lambda is velocity times time period, which means in each cycle the wave travels lambda distance. Now what is this velocity? What is the velocity of a wave? Well, it depends on what kind of wave it is, and also on what kind of medium wave is traveling. So let's say, for example, wave which is being supported on a string. So let's say there's a string, and this wave is being produced by an oscillator, and this wave is moving forward with the velocity v. For this kind of wave, velocity is given by root t over mu, where t is the tension in a string and mu, which is a Greek letter, is mass per unit length. What does that mean? It means that if you increase the tension, the velocity of wave increases, which means in a sort of sluggish rope, the velocity will be low. But if this is a very taut rope, then velocity will be high. Also, what is mu? Mu is the mass per unit length, which tells you how heavy or how light a rope is for each meter, or is it really a thick rope or a thin rope? So thick means like sort of heavy if you take a certain length of a rope, is it heavy or is it light? So let's say, for example, a rope like this may have a higher mu than considered to a rope like that, which has a lower mu. So a heavy rope, it's not really a good term to say heavy rope. You can say heavy per unit length, which means each meter or each meter of a rope. So a heavy per unit length, a rope with heavy per unit length will have a lower velocity of wave compared to a rope which is, or a string which is has a lower or light mass per unit length. Just to clarify, let's say if you have a rope which is 1 meter and there's another rope which is 1 meter. If this guy, let's say, is made up of cotton, but this guy is made up of, let's say, copper, and let's say they have the same thickness, but copper, this particular string or rope will have a higher mu than cotton. Or if you really want a different example, let's say you have a rope which is very thick, really thick, something like this, a very thick rope, and this is made up of cotton, and you have another rope which is made up of copper. Then it may happen that mu of cotton is more than mu of copper. So it's all about how much is the mass of 1 meter of rope. Okay, so this is mass per unit length. So velocity of a wave is given as square root of t over mu. T is the tension. Alright, there's another very known types of waves, and which are called sound waves. Waves which travel in air. Well, like the pressure waves we talked about, the pressure wave. And for sound wave, velocity is given as b over rho, where b is the bulk modulus and rho is the density of air. So these are two, and you can see these things change with respect to temperature. If temperature changes, bulk modulus of air as well as density of air changes. So velocity of waves in air changes with temperature. So this is the velocity of wave which will travel in air. Just to distinguish, this we already have said is transverse wave, and this is nothing but longitudinal waves. There are a few more things we can talk about, which is how does a wave reflects and transmits. So let's say if you have a string and you connect it with another string, let's say which is a little heavy in, it has a lower mu, it has a higher mu, and if you let a wave pass through this, if you produce a wave here by connecting it with an oscillator which is going up and down, then what happens? The wave travels forward, sort of enhancing the amplitude. It may not really be this high, it may be lower. And what happens? At the junction, there is a transmitted wave and there is a reflected wave. So this is transmitted and this is reflected. Okay, just to notice, you see the transmitted wave goes on like that, goes on, so transmitted wave goes on as the incident wave. So this guy was incident wave, this is incident wave, INCIDENT wave, and the wave which has transmitted is nothing but it just keeps going on as incident wave might have gone. But the reflected wave, you see, that reflected wave, let me draw this. This is the transmitted wave, and this is the reflected wave. But a reflected wave suffers a phase change of pi/2. What does that mean? It means if the initial wave was traveling, has this equation, a sine omega t plus phi, if that was the equation, the transmitted wave will just follow the same equation. So y transmitted will be nothing but some new amplitude, a1. It will have a different amplitude than the incident wave, so this is incident. But the transmitted will have a different amplitude, but will follow the same kind of sine wave. But the reflected wave, yr, will have a different kind of amplitude, and on top of that it will also suffer a phase change of pi/2. There will be additional phase which you have to add, and this is nothing but a cos of omega t plus phi. So you see, this guy just keep going like that, but this guy becomes a cosine instead. So these are called boundary conditions. So this is all about transmission and reflection and velocity of waves.